Sketching is one of the oldest and most natural ways for humans to express themselves. However, while it has become commonplace to control touch-enabled devices with gestures, there are no widely established ways of using digital pens for more than text input. We therefore believe that there is untapped potential in using sketching as an interaction modality and explored how users would express common operations on spreadsheets. Spreadsheets are used in a wide range of application domains, but are cumbersome to edit on tablets and other touch-enabled devices without a mouse and keyboard. We believe that sketching with a digital pen right on the spreadsheet might help users to interact with them more easily. To understand how users would like to interact with spreadsheets using a digital pen, we conducted an elicitation study designed to answer two research questions. First, how would users sketch common operations such as editing, formatting, and visualizing data, performing calculations, and changing the spreadsheet structure? And secondly, what larger patterns and strategies do users employ to sketch commands? The results of this study can be of value for designing visual languages to precisely express commands and building software components for correctly interpreting and executing those commands. Our elicitation study comprised a set of 20 tasks, covering a broad range of typical operations on spreadsheets, such as entering and deleting data, formatting and visualizing data, and making calculations. The tasks were clustered into 4 groups by their approximate difficulty to reflect the participants' increasing experience with sketching. The task order within the groups was randomized for each participant in order to avoid tasks biasing each other. We invited 36 participants from German and Icelandic academia and industry and asked them how they would solve these tasks by sketching with a digital pen right onto a simulated spreadsheet displayed on a tablet. In this reenactment of our study setup, a participant demonstrates how she would express her intent to move several cells to another location by inserting them and then drawing an arrow towards a destination. We categorized our participants' responses by analyzing how they expressed the action and parameter aspects of their commands. For each command aspect, we distinguished whether it was expressed textually, symbolically, by selection or a connection with another element, through an example, or by its location on the underlying spreadsheet. We also encoded if command aspects were implied or missing, or if participants preferred to express them through a graphical user interface. This way, we encoded each sketch produced by our participants, as shown in this example, where the movement of cells was expressed by an arrow from a selection to the intended destination. Different participants pursued different approaches to express the same commands visually. To create a pie chart, for example, many participants encircled the desired value set and drew an example of a pie chart. Despite this apparently straightforward solution, even more participants, however, wanted to work with GUI menus to achieve the same outcome, even though such menu structures are not commonly used on tablets. This is an indication of legacy bias, a common effect in elicitation studies where participants stick with a familiar interaction modality instead of employing the proposed new one. A few participants also preferred writing simple text commands to express their desired operations. Based on the categorization of all participants' proposals, we calculated agreement rates for all 20 tasks, using the methodology introduced by Vatavo and Woodbrook. According to their classification, most of our tasks showed medium to high agreement between participants. Some agreement rates were predictably high, such as deleting a value by crossing it out, or moving cells, as we've seen earlier. However, lower agreement rates often provided interesting insights as well. For example, participants proposed a rich set of patterns to express this repetition of an addition across columns, using arrows or selections, symbols, written commands, or plain duplication. Designers of visual languages and software tools need to balance the flexibility afforded by allowing multiple expressions for the same command with the ambiguity that the recognition algorithm may have to resolve. Just like the same command can be expressed in many different ways, the same sketch element can be interpreted in many different ways. Arrows in particular can mean operations as diverse as moving data, transforming data, such as transposing it, relating data to operations, repeating operations, continuing data series, selecting data ranges, expressing operations, or just decorating a sketch without carrying any operative meaning. The fact that you are probably able to understand the operations expressed by most of these sketches intuitively indicates what a powerful construct they are for visual language designers. At the same time, this expressive power poses significant challenges for a software tool's sketch interpretation logic. As an example of the semantic richness of participants' proposals, this participant solved a combination of addition and multiplication by defining labels for some values, which they later referenced in another part of the calculation. Many participants produced sketches that did not explicitly specify all command aspects, but implied either the action to be performed or some of the parameters involved. For example, this selection style strongly implies deletion of the selected content, and this pattern suggests that the values should be formatted as currencies. Finally, interpreting the single sigma symbol requires an understanding of the table structure and the convention that a sum is typically placed underneath all the numeric values in a column. While such expressions appear intuitively understandable by users, they are more difficult to interpret correctly for a software tool, as they require an understanding of the semantics of the sketch or substrate. Last but not least, we observed some participants who did not explicitly draw the relationships between the elements of their sketch, but relied on the temporal sequence of their sketch elements to convey this meaning. This participant, for example, first encircled the operands of the addition, indicated the operation using the plus operator, and then encircled the factor that the sum should be multiplied with, as indicated by subsequently drawing the times operator. In summary, we have observed that users express commands in ways that may differ quite a bit in their visual syntax. However, they employ rather coherent patterns for explicitly expressing command aspects, as well as strategies for implying common aspects, some of which pose interesting challenges for sketch recognition and interpretation logic. We occasionally observed strong legacy bias, as participants fell back to menus and dialogues rather than coming up with sketch expressions for commands that they were used to control through GUIs. Nonetheless, we believe that this could be overcome by introducing participants to sketches that are more efficient than menu-based approaches. We identified considerable potential for further research, such as exploring how sketching can be used to construct complex formulas or to iteratively refine visual artifacts such as charts. The construction of sketch recognition and interpretation engines that are aware of the structure and semantics of the document that's being sketched on likely holds interesting engineering challenges as well. Finally, and perhaps most excitingly, we believe that the combination of speech and sketching could be a highly efficient interaction modality, as it combines two of humans' most intuitive modes of expression. This work can serve as a first step in that direction. If you would like to learn more, please see our Chi 25 paper or contact us for more detailed information.